few kids asked me for the examples for more practice that you guys had for homework. I'm going to do those on PowerPoint, and then I'll also upload the PowerPoint, but I thought it might be useful for you to see me do the work and talk about what I'm doing. The first one is f of t. We're just going to do derivatives every time, so I'm not going to write the instructions, although I know you will. So t squared divided by the square root of t plus 1. The first thing that I'm focusing on is the fact that we're given a quotient of two functions. So the derivative of the quotient of two functions is the denominator times the derivative of the numerator minus the numerator, t squared, times the derivative of the denominator. And the derivative of square root is 1 over 2 times that square root. You could also use exponents. You could think of t plus 1 all raised to the power 1/2, but I'm not going to do that. However, there we go. So 1 over 2 times the square root of the input. That input is t plus 1. So you need to multiply by a 1, the chain rule. Maybe write that slightly differently. 1 plus 0 is the derivative of t squared plus 1. Divided by the square root of t plus 1 squared. So let's simplify this a little bit. The first term is going to be 2t times the square root of t plus 1. And the second term is going to be, how the heck will I write that? T squared over 2 root t plus 1 all over... I think the best way to go, still trying to write an x, is to split this into two pieces. And the first piece is going to be 2t over the square root of t plus 1. And the second piece is going to be t squared over 2 times the square root of t plus 1 cubed. Because there are 2 t plus 1 multiplied here, and one more square root of t plus 1 here. All right, number 2, maybe I should start numbering these. We're given f of x is x squared plus 1 over x cubed. This should make you happy. I'm probably going to do this a different way. Instead of the quotient rule, I'm just going to write f of x is 1 over x plus 1 over x cubed, which means f prime of x, I can just use the power rule, negative 1 over x squared minus 3 over x to the 4th. If you're wondering what I did there, I'm thinking of f of x as x to the power negative 1 plus x to the power negative 3, and using the power rule. You could also use the quotient rule, but this way is much easier. So z is equal to x plus 1 quantity cubed times 5 minus x to the 4th power. You could multiply everything out, but that's more of a hassle, so I'm just going to go ahead and use the product rule and the chain rule. First function, derivative of the second function. And you do have to multiply by a negative 1. The derivative of 5 minus x is negative 1. Okay, plus the second function times the derivative of the first. Squeeze a 3 in there. And the derivative of x plus 1 is 1. We are going to have to rewrite all that. So collect common terms. These both have a bunch of 5 minus x's. So 5 minus x, there are 3 of those at the most, and 2x plus 1s in both terms. Any common numbers? Doesn't look like it. So out of the first term, what would we be left with? Negative 4 times x plus 1. And out of the second one, that would be plus 3 times 5 minus x. Not good enough, actually. We're going to multiply and get, let's see, negative 4x minus 4 plus 15 minus 3x And what combines? How about 15 minus 4 is 11. Sorry, I'm just trying to think if I missed something. Minus 7x. I think that's right. I hope that's right. F of theta is 1 over tangent of 2 theta. So I really don't want to use the quotient rule, so I'll just rewrite f of theta as cotangent of 2 theta. And the derivative of cotangent of some angle is negative cosecant squared of that angle. Angle 2 theta has a rate of change of 2. Negative 2 cosecant squared of 2 theta. You could definitely do the quotient rule with tangent, but I think we can all agree this way is easier. Number 5, we're asked to find a second derivative, so that's going to be some more work. So 3x multiplied by 2 to the power of 5x. Deal with the product of two functions first. First function times the derivative of the second function. Let me go back and say that. The derivative of 2 to a power is 2 to that power, natural log of 2. The power is 5x, which has a rate of change of 5. So let's see, plus 2 to the power of 5x times 3. There's not a lot we can rewrite, but there is a little bit. And so in the second line, let's see, 15x times, let's rewrite that. 15 natural log of 2 times x, 2 to the power of 5x. Okay. So part of this next derivative, the second derivative of f, is going to be easy, and that's this last piece. In the first piece, 15 natural log of 2 is a constant, so I'm just going to group that with the x, because a constant times x has a derivative of just that constant. So 15 natural log of 2 times x times the derivative of 2 to the power of 5x has a derivative 2 to the power natural log of 2. Input of 5x has a rate of change of 5. Okay? Plus the second function, 2 to the 5x, times the derivative of the first, so 15 natural log 2. Okay. And then let's put brackets to show that was the derivative of this first piece. And 3 times a function gives 3 times the derivative of that function. 2 to a power has a derivative 2 to a power natural log of 2. Input of 5x multiplied by another 5. Let's collect all the common terms. Do these all have a common number being multiplied? They all have a natural log of 2 times 5 times 3. So I can factor that out, 15 times natural log of 2. And do they all have a 2 to the power of 5x? They do. Do they all have a natural log of, I already pulled out the 2. And so let's see what's left. So 15 natural log of 2 is left with another natural log of 2 times an x. Is that all? I think that might be all, because we pulled out 2 to the power of 5x. Plus, what's left from this middle term? Nothing, so that's just a 1. And then this last term, the 15 natural log of 2, pulled that out. Are these two the same? I think they are. So we can just make this a 2. I'm not sure if that's correct. Let me know if I screwed up. So f prime of beta, we're given f of beta, and that is beta y. And we have to assume y is some other function, so we're going to be using implicit differentiation. So beta is the input variable. We treat that like we normally would x. and denominator times the derivative of the numerator. So the derivative of beta times y, that's two functions. First function times the derivative of the second function plus the second function times the derivative of the first. The derivative of beta is 1 because beta is the input variable. That's what I meant by treating beta like x. And the derivative of y to the 6th power is 6y to the 5th power. Y is some other function, so we need a y prime. Okay, what did we do there? We did the denominator times the derivative of the numerator. Minus the numerator times the derivative of the denominator, oh no, which is -1, all over the denominator squared. There's not much interesting simplifying there. You can work on that if you want. I'm not going to put it here. So y is the natural log of 2t cubed. We're actually asked for dy dt. And we're actually taking the derivative of this natural log first, which has a derivative 1 over the input. That input is natural log of 2t cubed, which has a rate of change of 1 over its input, which is 2t cubed, which has a rate of change of 6t squared. And we can simplify a little bit to get dy dt is equal to 3 over t times the natural log of 2t cubed. Number 8, g of x is x times e to the x squared. Hopefully you see a product of two functions, which has a derivative of the first function times the derivative of the second function. The derivative of e to a power is e to that same power, natural log of e. Our power is x squared, which has a rate of change of 2x. Plus the second function times the derivative of the first. So what can we factor out of both terms? And e to the x squared. And we'll be left with 2x squared plus 1. This one you may want to avoid the quotient rule, so let's rewrite x of r using different notation. So 3r to the power 1/3 minus 3. Let's think about this. How could I write this? That's the square root of 3 times r to the power -1/2. That's the easiest way to go. And then plus 1/3 r to the power -1. So the derivative of 3r to the 1/3 is 3 times 1/3, or 1, r to the -2/3. And then over here we get to ignore our constant -3, so plus, or -√3 over 2 times r to the -3/2, we're using the power rule, minus 1/3 r to the power -2. So x prime of r is going to be r to the -2/3 power is 1 over the cube root of r squared plus √3 over 2 times the square root of r cubed minus 1 over 3r squared. Did you need that for longer? H of y is equal to cosine of y, that looks like cozy, over 1 minus sine of y. I don't really like the quotient rule there. I don't know, this seems right, so I'm going to do it. I'm going to multiply by the conjugate here. I think I'm going to get a nice division. So cosine y plus cosine y sine y over 1 minus sine squared. And 1 minus sine squared is something you should know. That's cosine squared. So, ooh, that's not h prime, that's still h. H of y is actually cosine over cosine squared is secant of y, plus, let's see, cosine, one of the cosines divides, and we're left with sine over cosine, which is tangent of y. If you do it that way, the derivative of secant y is secant y tangent y. Do I need a y prime? No, the input variable is y. Plus the derivative of tangent is secant squared of y. Z is equal to 10 to the power 2 log of x. Hopefully you know that without a base, it is assumed that the base of a log is 10. That's called the common log. So we rearrange and move that exponent 2 to be the exponent on the x. At this point, the 10 and the log base 10 are right next to each other, and they're inverse operations. We can say they cancel each other out. Really, we're finding the derivative of x squared. dz dx is 2x. That's much easier than using other rules. So number 12, this is going to be a long one. Sine with an input of cosine that has an input of tangent that has a derivative, an input of natural log of x. 2, 3. The outermost function is sine, which has a derivative of cosine of the same input. The next innermost function was this cosine, which has a rate of change of negative sine of the same input. The derivative of tangent is secant squared of the same input. That input is natural log of x, which has a rate of change of 1 over x. This is a negative out here. None of that can be simplified because not much has the same input. These things are all multiplied. I'm going to stop. So arctangent of 2 over t is equal to, what is that, f of t. So I'm going to rewrite f of t is arctangent of 2t to the power negative 1. That might make our lives easier. If you haven't memorized this, you're probably doing it a different way. The derivative of inverse tangent is 1 over 1 plus the input squared. That input is 2t to the power negative 1, which has a rate of change of negative 2 over t squared, or negative 2t to the power negative 2. We actually do have to rearrange this one because right now we have a power inside a power. So negative 2 over t squared times 1 plus, how are we going to write this thing? 2 over t. Okay, so actually this is pretty easy to do. What I'm going to do is multiply t squared times 1, which is t squared, and then 2 over t when squared gives you 4 over t squared. So t squared times 4 over t squared is just 4. So number 14, g of theta is the square root of 3 theta plus tangent squared of 4 theta. A lot of chain rule stuff here. Hopefully by now you've memorized that the derivative of the square root of something is 1 over 2 times that square root, also in the denominator. The input to that square root stays the same. So we need to multiply by, and this is going to end up in the denominator, the derivative of that 3 theta plus tangent squared of 4 theta. The derivative of 3 theta with respect to theta is 3. The derivative of tangent squared, 2 times tangent to the first power. And the derivative of tangent is secant squared, still of 4 theta, with a rate of change of 4. It looks like y. d prime of theta is, did I make anything better? Not much. 3 plus 8 tangent of 4 theta secant squared of 4 theta over that same 2 root. All that junk. What are we on? 15. F of x is x cosine of e to the x. Product rule first. The derivative of a product of two functions is the first function times the derivative of the second function. The derivative of cosine of something is negative sine of that something. R something is e to the x, which has a rate of change of e to the x, plus the second function times the derivative of the first. There's not much simplifying we can do. We'll just make it look a little prettier. So we're asked to find dy du. The derivative of something cubed is 3 times that something squared. The derivative of cosecant of 1 is 0, since cosecant of 1 is a constant. And the derivative of secant is secant tangent. And so we get 3 times cosecant of 1 plus secant of u squared times secant, I guess I don't need that, secant u tangent u. I don't feel like multiplying out this squared piece, and nothing interesting really happens, so I won't. Almost there. Number 17, g of z is az squared over a squared plus z squared. Z is the input variable, and a is assumed to be a constant since a is a letter at the beginning of the alphabet. The derivative of a quotient of two functions is the denominator times the derivative of a numerator, and don't forget this is a number times z squared, which has a derivative 2 times a times z, or z to the first power, minus the numerator times the derivative of the denominator. The derivative of a constant is 0, a squared is a constant, and the derivative of z squared is 2z, since z is the input variable. All over the denominator squared. Let's see, does anything combine? 2a cubed z plus 2az cubed minus 2az cubed. Oh, wow, that's interesting. Is that right? 2 times a times z times another z? Yeah. And last one, number 18. The derivative of a quotient of two functions is the first function, the denominator, I'm losing my mind, times the derivative of the numerator minus the numerator times the derivative of the denominator. Don't forget that chain rule on 2 plus x. And I'm just going to go ahead and square that cube. Ooh, do I want to multiply that out? Not really. Maybe I'll just factor. So factor out an x and a 2 plus x squared. And we'd be left with 2 plus x minus 3x over 2 plus x to the power of 6. I hope that helped.